here was a co-supervisor of Kamil's PhD thesis. He's a colleague of us from several years past, and very experienced researcher with machine learning, time series, biomedical applications, to name a few. I most probably miss a couple of important points, but you'll correct me. But generally, it's a person who is really worth listening for number of topics, and one of them is presented here, and it's connected with part of Krisztian's research work. Krisztian is right now with Jozef Stefan Institute, if I pronounce it correctly. It's an institute a bit like ours in form, and they don't have students, and they are research institute, government-sponsored research institute. The difference is that while in Poland we have a number of institutes, in Slovenia they have one, Jozef Stefan Institute. That's a very simple situation, if you think about. And actually, this is the key. To be honest, this is the only institution in Slovenia I have heard of from several sources as being the key research institute. Maybe there are others. I'm not maybe giving enough credit, but Slovenia is a smaller country and they are a bit more concentrated. So Krisztian also has an experience of working in industry and working in industry as a machine learning expert. So this is also something important, in the experience. So if you have, and Krisztian will be with us for today and maybe part of tomorrow. So if you have anything that you are interested in, you want to talk about something related to the presentation, or maybe something mentioned in the presentation, this is the occasion we have. The time today is a bit free, so don't worry that you will interrupt something, just come to us and talk. And this is a rare opportunity to have somebody outside in our domain of machine learning to get another perspective, to get some insight into the methods or general research work. So without further comments, Krisztian, I invite you to present.
So good morning, and thank you very much for Professor Blum for this beautiful introduction. It's a pleasure to be able to be here, and I thank you all for joining this talk. The title of this talk is Link Prediction in Bipartite Graphs and its Applications to Drug-Target Interaction Prediction. So this is what I'm going to talk about. And so in case if some of you are very busy and you have to check your emails during the talk or something like this, there is a slide which summarizes this talk in, let's say, 30 seconds. So this talk will be about a series of papers that have been published together with my collaborators, with Ladislav Peška from the Charles University from the Czech Republic, and with Julia Koller from the Semmelweis University from Hungary. And so if you cannot afford to pay attention to this talk, then it's enough to note that URL, which is on the top of the slide, then you can later on read these papers if you want. Professor Blom already introduced me, and I know that many of you already know me. However, I still included a slide about myself, just to give an introduction, who am I? And I think Professor Blom already said everything what was important. The only thing I wanted to mention is that I wrote my PhD about time series classification, and whenever I say the word time series, most of the people immediately think of time series forecasting, and time series forecasting is what you can see here in the left of the slide. However, this is not what is meant by time series classification. A typical example for time series classification is given in the right of the slide. So in case of time series forecasting, we want to forecast future values of a time series, and of course in case of an experimental setting, we work with historical data, so we already know what is the correct forecast, so we can somehow compare our forecasted values with the true values of the time series. And this is different from time series classification. In case of time series classification, the entire time series is given, and we want to classify those time series. This time series classification is the common denominator of various recognition tasks. So what you can see here is some time series from the domain of keystroke dynamics. In case of these time series, we wanted to decide which user typed those time series. So we wanted to recognize the user based on the dynamics of typing. So here we don't want to predict how long will the user press the next key, because the user has already typed whatever the user wanted to type, and based on her or his dynamics, we want to recognize the user, we want to identify the user, but we don't want to predict for how long will the user press the next key. So what I have been working on, this was time series classification and not time series forecasting. This is something that I wanted to note at the beginning of this talk. So if you have a look at my publications, there are some other publications which are somehow related to text mining as well. And one of them which I wanted to highlight was first authored by Alexandra Revina. She defended her PhD thesis in January. And the title of this publication basically says what it is about: IT ticket classification, the simpler the better. In case of this work, she showed that simple models like naive Bayes and nearest neighbor work surprisingly well in context of an industrial task, in context of a task for which we had the data from German Telecom. This task was IT ticket classification. We wanted to decide about some task descriptions, how difficult that task is. Task description could be something like install a printer or install a new antivirus software, and based on such descriptions we wanted to decide whether it's an easy or a complex task. And simple models worked surprisingly well. So now I would like to talk about the actual topic of this presentation, about drug target interaction prediction. So before I began to work on this topic, I naively thought that if I go to a pharmacy, to a drugstore, and I buy some medicine there, then whatever this medicine will do in my body, this is something that the medical doctors exactly know. However, I had to learn that this is not the complete truth. Because, of course, if a drug was designed to interact with some particular proteins, then this drug will indeed interact with those proteins. However, due to the large number of proteins in our bodies, even if the probability of interacting with a randomly selected protein is something like 0.1%, this drug is still expected to interact with some additional proteins. So why is this work important and interesting for us? Because we want to understand how drugs work, we want to understand better how drugs work. And it may turn out that some medicine which has already been used for a particular disease may be used for another disease as well. One of my favorite examples, which I usually explain to my students, is the case of Viagra, or Viagra, I don't know what is the correct Polish pronunciation. And why I explain it to my students is that this drug has originally not been designed to treat erectile disorders or anything like this, but this drug was originally designed to treat some heart diseases. However, it turned out that this drug was not effective in treating the heart diseases, but some strange secondary effects have been observed, and this was the reason why this drug was used for that kind of disorders for which it became famous. You know, this is kind of a funny example, and this is something that I used to explain to my students for a long time. And a few years ago I thought that, okay, now it's already time to be a little bit more serious, and instead of talking about Viagra, I would consider some more serious examples, just like the one you can read in the bottom of this slide. However, after that, I read in the news that this Viagra saved the life of a COVID patient. And this COVID patient was actually a woman. So it seems to be the case that this Viagra is quite useful for many things, except for that one purpose for which it was originally designed. So this is kind of the ultimate example of drug repositioning and drug repurposing. So I just can't stop me talking about it. If you consider this topic from a little bit different perspective, from the financial perspective, then you realize that drug development is extremely expensive. It costs about $800 million to $1 billion to bring a new drug to the market, and it takes a long time. So this means that even if we can improve it just a little bit, if we can improve this process by 1% or by 0.1%, this already means millions of dollars, and now this claim is about one single drug. So if we can improve this process by 1%, hopefully this will not only be useful in the development of one drug, but it may be useful for the development of several drugs. So I think that here there is a big potential for having a real world impact. Now, let us consider this task from the theoretical point of view, from the point of view of computer science. From the point of view of computer science, drug-target interaction prediction is nothing else but the prediction of links in a bipartite graph. The situation is the following. We have two classes of vertices. The first vertex class corresponds to the drugs. The second vertex class corresponds to the targets. These targets are proteins in case of drug-target interaction prediction. And some of the links are already known. That is, we know that, for example, this drug interacts with that protein. And there may be some additional interactions between drugs and targets. And based on the given links, we try to infer the probability of other interactions. We try to infer what is the probability of this interaction and what would be the probability of that interaction, and so on and so on. So in this example, I only plotted one missing link, but basically we try to estimate the probability of all the interactions. Of course, this is not only useful for drug-target interaction prediction. Instead of drugs and targets, you may talk about products and users. And perhaps you remember there was this famous Netflix competition in case of which we tried to recommend movies to users. That is also a similar problem, although in that case we wanted to do rating prediction instead of a binary prediction. In case of this Netflix competition, the task was to predict a score, how likely, something like between 1 star and 5 stars. And 5 star denoted that the user likes that film very much, and 1 star denoted that the user does not like that film so much. And you can also think about the relationship between users and blogs. So some of the users write comments on some of the blogs, and based on this, we may want to predict which blogs are interesting for which of the users. And today, instead of talking about blogs, we may talk about posts on LinkedIn or Facebook or wherever. But from the point of view of theory, this is basically the same task. This is just link prediction in a bipartite graph. Here, a more formal definition of the problem is given. So what we are given is a set of drugs. This is denoted by this calligraphic D, and we are given a set of targets. This is denoted by this calligraphic T. And additionally to that, we are given a similarity matrix between pairs of drugs and another similarity matrix between pairs of targets. In case of drug-target interaction prediction, these similarity matrices are based on medical background knowledge. In other cases, so for example, in case of this Netflix challenge, as far as I remember, some information about the users were given, like their age and gender and so on. So you could use this information in order to derive similarities between users and movies in case of that challenge. Or if you not even have that information, then simply based on the existing interactions, you can already calculate such matrices. So for example, you can calculate the Jacquard coefficient of two users based on its interactions with the items. And you can similarly calculate the similarity between two items based on its interaction with the users by calculating, for example, the Jacquard coefficient or cosine similarity or something like that. And once we are given this data, the task is to predict the likelihood of immune interactions. So how can we solve this task? We will now consider a set of solutions for this task, and the simplest solution is called weighted profile in the drug-target interaction prediction literature. In the literature about recommender systems, this approach is often referred to as nearest neighbor collaborative filtering. And what happens here is that for each of the drugs, now I'm telling the story from the perspective of drug-target interaction prediction. For each of the drugs, you select its nearest neighbor based on the similarities. And for example, if you selected 5 nearest neighbors, then you just average the interactions of those 5 nearest neighbors. And based on that, you will get an interaction score for the new drug. What is the likelihood that it interacts with particular targets? And you can not only do it from the perspective of drugs, but you can also do it from the perspective of targets. For each of the targets, you can consider the most similar targets, its nearest neighbors, and then you can average the interaction profile of those similar targets, and by averaging the interaction profile of those similar targets, you get an interaction score, a likelihood of interaction of this particular target with all the other drugs. So basically you take either rows of the matrix or columns of the matrix, of this interaction matrix, and then you average them. Is it more or less? Thanks. So, some other approaches for link prediction in bipartite graphs are based on matrix factorization. Here the idea is that we have an interaction matrix and we want to factorize this interaction matrix as a product of two low-rank matrices. These low-rank matrices may be denoted by U and V. And a possible solution for finding U and V is that we define a loss function such as mean squared error over the new instances of the interaction matrix. And we can add some regularization term to this loss function here. A simple L2 regularization has been added. And once we have such a loss function, we can simply use gradient descent to minimize this loss function in order to find the U and V matrices. However, if only positive information is given in the training data, this may be misleading, and this is what I want to illustrate on the next slide. So our bipartite graph looks somehow like this, and based on these bipartite graphs, we can write a few ones in our interaction matrix. So this is something like an adjacency matrix of this bipartite graph. So you can see that we have 4 columns and 5 rows. This is because we have here, in this example, 4 vertices in the first vertex class. So these vertices correspond to the columns of this matrix. And these other vertices here in the second vertex class of the bipartite graph, they correspond to the rows of the matrix. And so for example, this one denotes that the third vertex is connected with the first vertex from the second vertex class. So this one here. This representation by design basically only contains ones and missing values. However, if this interaction matrix only contains ones, then there is a danger that the learning algorithm will learn that every item of the interaction matrix is simply 1 because it only observed once in the data. So in order to make some reasonable prediction, a simple approach is that we introduce some fake zeros. So we just randomly set some of the missing values to zeros. Then we can execute matrix factorization, and then this matrix factorization algorithm will output an estimation for the remaining missing values. Of course, we are not sure whether these values are really zeros. What we can do is that we just repeat this process several times with a different selection of those random zeros, and then in the end we obtain an estimation of the missing values in this matrix. Approaches based on matrix factorization are very popular in the domain of recommender systems, and with one of my collaborators, Ladislav Peška, we began to work on adapting these approaches to drug target interaction prediction. One of the most successful approaches in the domain of recommender systems is called Bayesian personalized ranking, and this is a typical matrix factorization approach. The idea is that we want to factorize these matrices in a way that the estimations for the given zeros should be greater than the estimations for the missing values. So what it tries to optimize is the ranking. So whenever you consider, for example, one of the targets, it should produce a ranking that it should rank the drugs in a way that the drugs for which an interaction is given should be ranked before those drugs for which the information is missing. And this can also be done the other way. So whenever you consider a drug, the targets should be ranked in a way that those targets for which an interaction is given should be ranked before those targets for which the interaction is unknown. And this BPR was a successful approach in the domain of recommender systems. However, in its original formulation, it only works on the interaction matrix and does not take into account the similarities between drugs and targets. And in case of drug-target interaction prediction, we have this additional information. We have this pairwise similarity matrix between targets and pairwise similarity matrix between drugs. So our approach was to extend Bayesian personalized ranking with taking this additional information into account. In particular, we took this information into account in form of some additional regularization terms. And finally, we could show that our approach worked better than the original BPR, than the original Bayesian personalized ranking. To say it a little bit more exactly, just to show you the problem formulation, what we are given is an interaction matrix, and what we want to find is a factorization of this interaction matrix so that the new interactions are ranked before the unknown ones, and this was our innovation, the low-dimensional representation of similar drugs and similar targets should be close to each other. So we not only wanted to find a good low-rank representation in terms of giving a nice ranking for the interaction matrix, but we also wanted to pay attention that so basically the rows of this matrix can be considered as a low-dimensional representation of targets. So you can see that in our interaction matrix there are 5 targets and 4 drugs, and here we have 5 rows of this U matrix. And each of the rows of this U matrix can be considered as a low-dimensional representation of each of the targets. And similarly, each of the columns of this V matrix can be considered as a low-dimensional representation of the drugs. And what we wanted to do is to find the factorization in a way that whenever 2 drugs are similar according to the given similarity matrix, which was given based on medical background knowledge, then the low-dimensional representations should be close to each other. And finally, we managed to do that, and we are happy that it worked nicely. Another approach for drug-target interaction prediction is called bipartite local models. This was originally introduced by Blakely and Yamanishi. Here the idea is that for each of the drugs, you train a local model, and this local model has the task to be able to predict interactions of that particular drug. So for example, if you train a local model for this drug DI, then you can and you want to predict this interaction between the J's target and the I's drug, so you want to predict this interaction, then what you can do is that you train a local model for drug DI. You consider these other targets as training data. For those targets with which this drug DI interacts, you set its label to 1 by saying that yes, this is a positive interaction, there is an interaction. And for the other targets for which the interaction is unknown, you set the label in the training data as -1. And then you train a model, and then this model is used to predict the likelihood of this interaction between the ICE drug and the JACE target. And of course, this is very demanding to do it for each pair of drugs, so you can do it a little bit more smarter, that you not just consider a single drug in your test set, but you consider, let's say, 20% of all the targets in the test set, so you want to make predictions for 20% of the targets. But this illustration tries to illustrate the idea behind bipartite local models. So this is the way how you train a drug-based local model, and in a similar way you can train a target-based local model. For each of the targets you can train a local model, and whenever you want to train a local model for target for the JACE target, for target TJ, then you consider the interactions of target TJ with all the drugs, and so if you want to make a prediction for this interaction, then you just consider this as a positive example, and this as a negative training example, and that one as a negative, and so on and so on. And once you have this training data, you can train your local model, and this local model delivers the likelihood of interaction for this interaction, for this possible link. In the original version of bipartite local models, Blakely and Yamanish used a support vector machine as a local model with a somewhat special kernel. And we thought that we tried to do it a little bit better. And instead of using a support vector machine, first we tried to use so-called hardness-aware regressors as local models. And then we introduced an approach which we called Aladdin. This Aladdin stands for Advanced Local Drug Target Interaction Prediction, and the main idea was to use a hardness-aware regressor as local model, and additionally to that we enhanced a little bit the representation of drugs and targets, and we used the projection-based ensemble. So let's have a look at these ideas in more detail. What is hardness-aware regression? This is a version of nearest neighbor regression, so this is kind of an advancement or an enhancement of nearest neighbor regression. And what is nearest neighbor regression? This is illustrated on the left of the slide. So here you are given some training data. This training data is denoted by these blue dots, and the training instances are labeled either as 1 or as 0s. And you want to make a prediction for this test instance, which is denoted by this yellow triangle. And you can consider its nearest neighbor. So if you consider one nearest neighbor, then you would say that, okay, the label of this yellow triangle will be 0. Instead of considering one nearest neighbor, you could consider 3 of its nearest neighbors, and then you would observe that one of the 3 nearest neighbors has a label of 0, and 2 other of the 3 nearest neighbors have a label of 1, so you could average these nearest neighbors, and then you could say that the prediction for this instance would be something like 0.33. This is because we are doing regression and not classification. But that will be standard nearest neighbor regression, and instead of considering the standard nearest neighbor regression, we can take into account the interesting phenomenon of hardness. I will not talk in detail about this interesting phenomenon of hardness, because as far as I remember, 7 years ago when I was here at this institute, I talked about hardness, so I want to skip the details. Now the idea is that we consider for which instance, so the idea is that we observe that the nearest neighbor relationship is an asymmetric relationship. For example, the nearest neighbor of this instance is that instance, however, the nearest neighbor of that instance is not this one, but another one. So this is an asymmetric relationship. And because the nearest neighbor relationship is an asymmetric relationship, we can count how many times an instance appears as nearest neighbor of other instances. So for example, this instance appears as nearest neighbor of 3 other instances. And then what we do is that instead of using its own label in nearest neighbor regression, we use something like an aggregated version of the labels of those instances for which this central instance appears as their nearest neighbor. This is the basic idea behind counter-severe regression. And this was one of the components of our Aladdin approach. The other component was to use an enhanced similarity-based representation of both drugs and targets, and this is illustrated here. You can see that, for example, so this will be the enhanced representation of the first drug in this example, and this representation is composed of the similarity of this drug to other drugs. So this first half of the representation, the first half of the vector belonging to drug number 1, just contains the similarity of drug number 1 to all the other drugs, and based on the medical background knowledge. And the second half of this representation is the similarity of this drug to all the other drugs based on the given interaction matrix, based on calculating the Jacquard coefficient between this drug and other drugs. So for example, this drug number 1 and drug number 2, they share one common interaction, and then if you calculate the Jacquard coefficient between these two vectors, then this would be 1 divided by 3. So this is the reason why here there is the 0.33 in this representation of drug number 1. In a similar way, we can represent targets in a high-dimensional vector space as well. And once we have this, then the last component of our approach was to perform some random projections. So instead of actually considering this representation of drugs and that representation of targets, we just selected some of the columns randomly, and then we trained a local model with Hubner-Severe regression. And in another round, we selected some other columns randomly, and again trained a local model. And finally, we just averaged all the predictions, so this was some kind of an ensemble approach. Now the last technique I want to show for drug-target interaction prediction, this is what we call Molière. This is the abbreviation for modified linear regression. And here the idea was that in reality, so reality is not binary. It's not really the case that a drug interacts with a protein or not. This is not a yes-no type of situation, but we can measure something like the energy of binding, so how strong these two molecules bind to each other. And because of that, we can say something like, if the prediction approach says that I think there is a very strong binding, we don't want to punish this approach for that, especially if there is indeed a binding. So it could happen that for some of the interactions the binding energy is relatively low, for other interactions the binding energy is relatively high, and the prediction approach may recognize it somehow. So it could happen that the prediction predicts something like, I don't know, considering the situation that you code the existing interactions with +1 and the non-existing interactions with -1, it could happen that the prediction approach predicts something like 5, because this prediction approach says that I am very certain that there is a very strong link between these two drugs. And this could happen, that the prediction approach is indeed right. So here the idea was that whenever there is really an interaction and the prediction approach predicts a score which is greater than 1, then we say that there is no error. And whenever there is indeed no interaction, or the interaction is not known, and the prediction approach predicts a score which is lower than -1, then we again say that this is not an error. And in all the other cases, we just use the simple mean squared error. And this gave us the following mean asymmetric loss. And we could minimize this loss with stochastic gradient descent. and this gave us the approach which we called asymmetric loss linear regression. And we use this asymmetric loss linear regression as local model within this bipartite local models approach. And so this was our last publication. So out of all the techniques that I presented so far, this was the one which gave the best results. And this result, and we evaluated these results according to standard machine learning protocols like cross-validation, and according to the standard evaluation criteria in this drug-target interaction prediction domain, which is area under a receiver operator characteristic curve and area under precision recall curve, because this is an imbalance classification problem, and in case of imbalance classification tasks, many authors argue that area under a receiver operator characteristic curve is somewhat misleading, so you should not only use AUC, but you should also use this area under precision recall curve, so you used this evaluation metric. And the most nice thing about this project was that we could not only show that our predictions are a little bit better in terms of AUC and AUPR, in terms of the standard evaluation metrics, but we could deliver some interesting hypotheses, which are interesting from the point of view of medical, which are medically interesting, which are interesting for doctors. And these hypotheses were formulated by Julia Kohler. She is a medical doctor who participated in our joint work. And I will not show these hypotheses because they are written in the paper, and you are all computer scientists, and I am a computer scientist, so I myself would not be able to really explain those hypotheses and why they are really interesting and important. So instead of those medically relevant hypotheses, I just show you one of our fun predictions, and this refers to the drug called caffeine. This is the drug that all of us consumes every day in form of, or perhaps not all of us consumes every day, but many of us consumes this drug relatively frequently in form of coffee. And what happened with caffeine was that some of the interactions of caffeine were given in our database, and based on these given interactions, we could predict some new interactions that were not given in our database. And the interaction that was predicted to be the most likely was the interaction with this cystic fibrosis transmembrane conductance regulator. This is the name of a protein. This was not in our database, and then we Googled whether this interaction between caffeine and this protein is already known or not, and it turned out to be a known interaction, so others already published this interaction, which is a nice story for us because it shows that the predictions of our approach are indeed reasonable. So finally, I am coming to the end of this talk. In this talk, I try to present you some approaches based on local models for link prediction in bipartite graphs. We considered the application of drug-target interaction prediction, which I think is the most prominent application of machine learning in the pharmaceutical industry, and I think it is in general one of the most prominent applications of machine learning. And of course, I hope that these approaches will be and can be applied in other cases as well. And I hope this presentation is not the end of the story, but the beginning. So perhaps you will have some interesting applications, and perhaps you want to predict links in your graphs, and then you can think of these approaches. Finally, I would like to thank you very much for your kind attention, and if you have some questions, please feel free to ask them.
I have questions. First one is related to the similarity matrix. Maybe I missed it, but these are based on medical observations?
Yes.
Okay. So our results are strictly related to some databases or medical databases, right?
Yes. Yes. So when we define this, you mean these matrices as SD and ST. The targets are proteins, and this protein similarity matrix in particular contained the so-called Smith-Waterman score, or some normalized version of the Smith-Waterman score. The Smith-Waterman score can be used to compare two protein sequences. Are you familiar with the Smith-Waterman score, or shall I say a few more words about this? Do you know
Please elaborate a bit.
do you know Levenshtein distance?
Yes.
Yes. So basically, this is the same as Levenshtein distance, but somehow in the domain of binary format, conceptually it's the same as Levenshtein distance. Okay. The details and maybe a little bit different, but conceptually it's basically Levenshtein distance on the protein sequences.
So it does not consider like the shape of the protein.
It does not consider the shape of the proteins. Yes, you are completely right. That's something that should be incorporated in the similarity matrices in state-of-the-art prediction techniques. So that is a very valid point for room of improvement.
Are there many proteins that have the same, let's say, length and vastly different properties? I don't know. I don't know anything about proteins. So.
I know really little about proteins, so don't take me as. But it's the case that if you have a protein and it's shaped one way or the other way, it functions differently. And it was a big challenge at some point to add that information. So first, everybody considered the protein just as sequences, and then there was the point that it can fold, and there was like this folded home and so on. So people exploring that. So I was just curious whether they already incorporated that or not.
So in that database which we use, it was not yet incorporated, and as far as I know, people try to do works into that direction.
It's not for us, I mean it's for those who work in that field to do it. So
there is an indication of what you're saying is there's an indication that there might be some proteins that by the measure presented are very similar, but that they are in fact very different.
Could be. It could happen that some of the proteins are similar according to this metric, but they function differently. This could happen for sure.
okay. Kamil, it's the end of your question? Or
Yeah, my second question, did you consider something like graph neural networks or convolutional networks or something like that?
Not yet. But Facebook just recommended an article about graph neural networks to me this morning. And I made a screenshot of this because it disappears from this list of posts, and it's on my to-do list to consider them.
I have a question. Because this problem is related to graphs and bipartite graphs, so there are a few approaches which are considered standard graph problems or standard graph solutions. For example, community detection. Where you try to estimate communities based off multiple graphs connected into a singular. Is this solution of yours, I mean the matrix decomposition solution, somehow related to this problem? And the second question is the other approach is searching for a stationary state of random walks in a graph, and it seems like this is somehow connected to spectral methods used on graph weight matrices.
So, to answer the first part of your question, depending on how exactly you formulate this matrix factorization problem, as far as I remember, if you formulate this matrix factorization problem with simply the mean squared error, then the factorization that you receive is said to be somehow very similar or equivalent to k-means clustering. So what does it mean? So for example, this row of this matrix can be considered as a low-dimensional representation of the first target, and the first column of this second matrix gives something like a fuzzy membership in the two clusters for this particular target. So this matrix factorization is indeed related to clustering, which is basically community detection.
Yes.
So clustering of graph nodes would be community detection in graphs. What was the second part of the question?
Because this also looks like spectral methods used when you are searching for a stationary state of random walks in a graph. Because you can use random walks in the graphs to explore the graph, also to estimate new edges in a graph. And you can search for a stationary state of the random walk. And it seems somehow similar to this.
Sorry, I'm just not an expert of random walks on graphs. So
Okay.
everything that I know about random walks on graphs was a classic PageRank algorithm that I learned while I was a student. So
Okay,
probably there are something more
so from the other point, is this somehow connected to min-max average cut of a graph?
Not that I know, perhaps.
Perhaps you can discuss it later on,
Okay.
because it
Okay,
may be something interesting for both of us.
perhaps you can say, because it seems somehow related, and I would not be surprised if this concept is up to the concept they were somehow similar, because when you are searching, when you are using matrix factorization, it seems that you will find a solution that is somehow similar to this one.
Yeah, that would be.
Okay. Never mind. I have actually another question. This is
I feel myself like in a PhD defense. No, sorry.
If you were at the PhD defense, we would speak in Polish and you have to ask in Polish.
Okay, rozumiem.
This question is not about graphs, actually, but about approach to problems. It seems to me that often when approaching difficult problems, you use in a clever way you use classic approaches or classic methods.
Yes.
For example, nearest neighbor.
Yes.
And I actually very like this approach. I somehow found out that these simple, maybe not simple, but well-known approaches often perform surprisingly well.
Yes.
And I would like to know your opinion about using them in practice, and I mean in industry. When you have practical problems, when you must solve for people who make money on the solutions, how would you weight complicated but state-of-the-art models like neural networks and simple solutions like nearest neighbor? Somehow we think, our intuition is that these simple solutions would be at disadvantage. However, it seems not always to be the case.
So of course it's difficult to talk about this in general because industry may refer to many different things. There is a substantial difference between developing some kind of a recognition system for a self-driving car, which is supposed to recognize traffic signs or pedestrians or whatsoever, or classification of these IT tickets which describe these maintenance tasks like install the printer or change the cartridge in the printer or install the new antivirus software and so on. So of course it's kind of difficult to talk about this in general, but my personal general feeling is that if I have a new industrial task, I will definitely start with something simple to solve it, and I will see how far we can get with that simple solution, because simple models can be understood relatively simply, and you can understand, if they fail, then you can understand why they fail, and you may tailor the final solution so that you kind of correct the errors of that simple model. And the other thing is that you mentioned neural networks under one umbrella, but of course there are many different neural networks. So there is, let's say, a simple neural network which has I don't know, 3 convolutional layers and an output layer. This would be neural network number 1, and there may be these really deep architectures which have dozens of hidden layers. And so for image processing tasks like detection of traffic signs and images, I'm not sure if nearest neighbor would be the appropriate approach.
Of course, there are some problems which are already solved, I would
Yes.
say.
But even in that case, I would rather consider first some simple neural networks, let's say a simple convolutional network with 3 layers, or even with just 1 convolutional layer or 2 convolutional layers at the beginning, and then I would somehow see what is the added value of adding more and more layers.
And what is your practical experience? How far you had to go in the in the past? I mean, how often it happened that you can actually stop on one of the simpler solutions? How often their performance was satisfactory?
I don't know, I'm not really the person who really made these decisions of whether to stop here or not. So, of course, there is one thing of delivering a product. Like, so if you are a startup and with, I don't know, 5 people and you want to deliver a product to a customer, this is one setting. And another setting is that if you work as something like a research group of a big company, then they may be interested in exploring the possibilities. Okay, we already may have some solution which is kind of okay, which can be integrated into a product, but we are interested whether we could achieve something substantially better with a more complex model. And I worked rather in this second type of setting where we were a research group within a big organization and not so much in that setting where, yeah.
Thank you.
Any more questions?
I have some questions actually.
First of all, thank you for the presentation. And well, it was an elegant presentation. I really like the way you explained the complex concept, but my special favorite is the hardness side, because hardness is a notoriously difficult subject to explain. And I know it because I have tried several times to do it, and we had internal discussions about that, and it was really not simple. This way of presenting is really very nice. Okay, so my first question concerns the database or databases. You say that you use a database to get this information from the matrices.
Mm-hmm.
So my question is, first of all, is it just one big database of all the drugs and targets, or there are several databases which are domain specific, for example? And how big those databases are? I mean, how many nodes do you have and how many links and so on?
So there are several drug-target interaction databases. In our work, we used 5 drug-target interaction databases. 4 out of these 5 drug-target interaction databases were from a classic repository, which were introduced by Blakely and Yamanishi. So they published some data which was related to their seminal paper. And this kind of repository contains 4 different drug-target interaction databases. The one contains enzymes, the other one contains nuclear receptors, the third one contains ion channels, and I just forgot the 4th one. And additionally to these 4 classic databases, we use the 5th database as well in our research, and there are many other drug-target interaction databases. In order to evaluate the machine learning approach, this was okay to use these standard databases. If the primary goal, and it was even enough to demonstrate that it is possible to generate some medically interesting hypotheses. But if you really want to seriously do drug-target interaction prediction, then you may need to use more serious databases than what we have. And I'm not sure about this, but what I heard about this recently is that the really serious databases are not public. They are private in the pharma companies. So
How big they are, those available ones?
these available ones, they are relatively small databases. They contain a few hundreds of drugs and a few hundreds of proteins. So whatever I have shown here and now, this is something that you can run on a PC.
Okay, my second question is about the relationship. Can you go back to the first slide when you have those definitions of matrices and so on? Yeah, this one. The question is, how do you deal with different levels of information? For example, you have a drug or a protein similarity matrix. So you take this Lederstein distance or whatever it is called, and you say, okay, those two proteins are similar.
Yes.
And this is basically, some could say it is an inference, some could say it is guessing.
Mhm.
And then you have an interaction. An interaction is something I assume that is observed. For
Yes.
example, so it's a stronger information.
Yes.
Is it, so you have to just pose the question, the weak information in this like ST matrix and strong or important information in this interaction matrix.
Mhm.
Do you take any effort, or is it in general, not only in your methods, is there any effort to weight those, for example, to, I don't know, get smaller weights for the target similarity and or more weight for interaction?
So when we incorporated this similarity matrices into matrix factorization, we unfortunately I don't really have the formula on this slide for our loss function, but I mean I can try to search for it on the internet if it's necessary. The way how we incorporated these similarity matrices was that we added some additional regularization terms to the loss function, and of course these regularization terms had a regularization weight, had this regularization hyperparameters, and these were hyperparameters of the approach, and we did proper hyperparameter search by splitting the data into training and validation and test subsets and so on. So this way, we somehow took into account that the different sources of information may have different weights, because if it turns out that those similarity matrices are not so important, then the regularization term will have a lower weight in the end, because of its regularization weight would be set to a lower value.
Okay.
But this may not be the best way of taking into account this kind of uncertainty.
Okay, the last question is simple. Of all the papers that you have posted on this second slide, yes, this one now. Which is your favorite? I mean, if you're supposed to read one, which would you recommend? Not in terms, of course, of carrying on the research, but generally to get like a background intro. Which would you say?
I would say you should read the most recent one. So this Molière, this modified linear regression. This is the most recent out of these papers, and if you read this one, then the related work already gives you a feeling about the other three as well. I think this was a nice paper, in my opinion.
Okay, thank you. Yeah, any more questions? No, thank you.
Thank you.